So let's now turn to Newton's universal law of gravity. And believe it or not, I think I even give you on the exam the gravitational force of Newton's universal law of gravity. I don't think you need it, but you will find it on the exam. Let's take the Earth going around the sun, and let's approximate the orbit by a circle. So here is the Earth, here is the sun, mass sun, and the orbital radius is capital R. The Earth has an orbital velocity, I call it v orbital, and there is on the object, the angular velocity, say, is omega. It goes around with a certain angular velocity, and there has to be here a force on the system, the gravitational force, which is the same as the centripetal force. That's the only way the object can go around in a circle. So this gravitational force equals mass of the sun, mass of the Earth, times g divided by r squared, the force of gravity. But it also must equal to the centripetal acceleration, and this is here the mass of the Earth, and so it also is the mass of the Earth times the orbital speed, v squared, divided by the orbital radius, and if you prefer to write that in terms of omega squared r, that's fine too. Look at this here. You lose your Earth mass if you want to know what the orbital speed is. You lose 1r, and so you find that the orbital speed equals the mass of the sun times g divided by r to the power 1/2, and that is about 30 kilometers per second. I give it in kilometers per second, but of course, when you calculate it, make sure you always stay in MKS before you make a conversion to other units. So you know what the period is to go around the sun. That is 2 pi r divided by the orbital, and that is about 365.5 days. That's 1 year. That's how long it takes us to go around the sun. Now I wonder, what is the kinetic energy of the Earth in orbit around the sun? Well, that's completely trivial, you would say, because it is 1/2 of the mass of the Earth times the orbital speed squared. Indeed, that is not very difficult. So the kinetic energy of the Earth in orbit equals 1/2 mass of the Earth times v orbit squared. So I take this equation and I square it. I lose the half there, and so I get m Earth, m sun times g divided by r. That is the kinetic energy in orbit. But that, oh, there's a half here. Whenever I make a slip, you should always interrupt. So there's a half here. This is also minus 1/2 the potential energy. And remember, the potential energy equals minus m sun, m Earth, g divided by r. So here you see plus half, here you see minus 1, so this is indeed minus half the potential energy. What is the total energy of the Earth around the sun? That means the sum of potential energy and kinetic energy. Well, the kinetic energy is minus 1/2 u, and the potential energy is u, and so this is plus 1/2 u. That means it's negative, because u itself is negative. It is also equal to minus k. I just calculated for fun how large that number is. It's a negative number, how large that is. And it turns out to be approximately minus 2.7 times 10 to the 33 joules. Deeply negative. Now, if we get bored and we want to leave the solar system, then we can ask ourselves the question, if we mount a rocket to the Earth and we fire that rocket, how much speed should we give it to get away from the sun once and for all and never come back? Well, all we would have to do is make the total energy of the Earth 0. So it can cruise all the way to infinity and have 0 speed when it gets there. How can I make this 0? Well, I have to add to the kinetic energy exactly k, because minus k plus k is 0. If I have to add the kinetic energy k, then the new kinetic energy after the rocket burn would be exactly 2k. The potential energy is not changing, because you fire the rocket when you're there, and so you're still at the same position after the rocket fire, and so your potential energy hasn't changed, but your kinetic energy must have doubled. If it hasn't doubled, this doesn't become 0. Aha! But if the kinetic energy has doubled, then the speed must have gone up by the square root of 2, because kinetic energy is proportional to v squared. So the escape velocity that you need must be the square root of 2 times the orbital velocity. And that would be for the Earth the square root of 2 times 30, which is about 42 kilometers per second. So by looking at the energy considerations, you can find the connection between total energy, escape velocity, and make the whole picture internally consistent.